I'm A.Fedotova, and I'm studying the variation in abyssal hill geomorphology in the South Atlantic Ocean. So abyssal hills are the features of the oceanic crust that run parallel to the ridge crest. There are two opposing theories regarding abyssal hill formation. The first being that spreading rate accommodated with faulting creates these hills. However, a more recent understanding is that orbital eccentricity cycles drive sea level fluctuations, which in turn drive the overlying lithostatic hydrostatic pressure at the ridge to fluctuate, and this affects abyssal hill dimensions. So in this study, I'm comparing these two theories. In order to qualitatively describe abyssal hill dimensions from multibeam data, I employed the methodology of Goff and Jordan in 1988. I divided the data set into boxes, which I then related to a covariance function, and through inversion I received the output abyssal hill scaling parameters, which included root mean squared height and characteristic width. So in this figure is from Goff et al. 2010. He predicted global abyssal hill root mean squared heights, and he said that in this particular spreading corridor, the abyssal hill heights are anomalously low compared to the rest of the southern Atlantic Ocean. When I overlaid my data over his, I found my results to be consistent with his. So abyssal hill formation times in this transect also do not appear to maintain a dominant duration. In this figure, I have the time to formation in blue and the half spreading rate in orange plotted against the age of the crust. So we can see that as you move through the crustal age, the time to formation fluctuates greatly between 100 to 500,000 years, and it does not maintain a preferred duration at 400 nor at 100,000 years, which are the frequencies that orbital eccentricity tends to operate on. We were expecting an inverse relationship between spreading rate and the time it takes to form an abyssal hill, and we're kind of seeing that in some parts of the plot. However, at 30 million years, there's a significant increase in the time to formation with only a small decrease in spreading rate. And we were wondering why that magnitude was so different. In the plot below, I have plotted abyssal hill root mean squared height versus half spreading rate and the age of the crust. And at 30 million years again, we're seeing only a small increase in abyssal hill root mean squared height with the small decrease in half spreading rate. So we weren't sure why the magnitudes of these two parameters aren't equal. A possible explanation to this can be found in a study Buck et al. 2005, who suggested that when half of plate separation is accommodated by diking out the ridge, fault offset is very large and therefore abyssal hills are wider. Now, while we can't monitor the exact magmatic output for millions of years ago, Skipwith et al. Suggested that there's drastically increased volcanism at 30 million years in this transect. So the red line is volcano abundance, and at 30 million years, there's a significant spike. High volcanism may suggest that seafloor spreading is being accommodated by less structural extension relative to magmatic output, causing wider hills but lower hills, which is what we're seeing at 30 million years. In order to test the climate hypothesis, I compared the bathymetry and the orbital eccentricity for two areas of the transect. The first has an abyssal hill duration formation for about 454,000 years. And so the bathymetry nicely lines up with a 400,000 year orbital eccentricity cycle, not so much a 100,000 year orbital eccentricity cycle. In the figure below, the area has abyssal hill formation durations of about 240,000 years. So neither the 100,000 year orbital eccentricity cycle nor the 400,000 orbital eccentricity cycle does line up with this. So this is kind of spotty related to the time to formation. I was comparing this to Tolstoy 2015, who did the same thing in the Southern East Pacific Rise. And she found a correlation between the 100,000 year orbital eccentricity cycle and the bathymetry. This is possibly due to the effects of orbital eccentricity varying at higher spreading rates and higher magmatic output. So our study suggests that both spreading rate and magmatism are significant factors an abyssal hill formation. We hypothesize that there may be a threshold at which the amount of magmatic output becomes dominant over spreading rate in influencing abyssal hill dimensions. Thank you.